let's go through astrology. We start from luminosity and radiant flux. So first of all, defining luminosity. So luminosity L is defined as the total power output of radiation emitted by a star. Okay, so that means a star, how much power is given out. How much power is given out. So that is luminosity. Of course, when we say power, the unit will be watt. So luminosity, the unit is watt. And then what is radiant flux intensity? So let's see the definition. The symbol is F. The observed amount of intensity or the radiance power transmitted normally through a surface per unit of area of radiation measured on Earth. So measured on Earth, try to imagine that. So for example, a scientist is staying on the Earth, looking at the star, and then try to find out the intensity of the star, and that is the radiant flux intensity. Okay. So let's say I give you a bit more details. Okay, let's say I have a star here and try to draw it out. So I have a star here. So the star is emitting the light in all directions. So basically you can imagine there is a sphere. Okay, there's a sphere. I put a sphere here because it emits light in all directions. Okay, so let's say it's up, left, here, there, front, back, down, everywhere. Okay, in all directions. So let's say you try to imagine in this scenario, so they are like forming a sphere. So a sphere has an area of surface area. A sphere has a surface area of A equal to 4 pi r square. Surface area of the sphere is 4 pi r square. Okay.
Is this whole thing a star?
The star is just this part, the middle. Then it emits the lights in all directions. And try to imagine there is a sphere that have a particular surface area. And we want to talk about this surface area, right? Because if we have the Earth over here, for example, the Earth is here, you won't detect the power from all direction. Let's say the lights here is not reaching the Earth. Okay, this light is not going to the Earth, and so on. So we can't check the luminosity directly. We can only check the radiant flux intensity. It's just a part of the light that reached the Earth. Let's say only this arrow reached the Earth. So we can only check this. Okay, so that is radiant flux intensity. The idea is there. Okay, so what happened again? You see the definition again. The radiant power transmitted normally. This is the one transmitted normally to the Earth through a surface. This is the surface. The sphere is the surface. Okay, per unit of area. So it's power per unit area. So basically, try to imagine it's something like this. Based on the definition, it's power P per unit area A. So where the A is 4 pi r square, as I discussed up there. So it's the surface area of a sphere. Okay. And then equal to, power is energy over time, so I can change it to energy, E over time, T, and then the area, I remain it at the bottom, area A. So this is the concept of radiant flux intensity. Okay. So that is the idea. Radiant flux intensity, which is the amount of intensity observed, and then it's based on this formula: power divided by surface area. Okay, so now we look at the next point then. The best way to picture this is the luminosity is the total radiation that leaves the star. So that is the luminosity. Like what I said, the star will emit power or emit lights in all directions. That is luminosity. The radiant flux intensity is the amount of radiation measured on Earth. So this is the Earth. Only the lights in this direction reach the Earth, and that is radiant flux intensity. Radiant flux intensity, you can imagine that it is just this one. It's just the green color one. It's just this.
It's 3 o'clock.
Luminosity is all this, all the yellow arrows are luminosity. Radiant flux intensity is just one of this. So by the time the radiation reaches the Earth, if you have spread out a great deal, so that means you see they spread out in all directions, passing through a long distance, and therefore it will only be a fractions of the values of the luminosity. I'll try to imagine. So this one arrow, right, is a fraction of the whole yellow arrows. Okay, it's just a small part. This is just a small part. The radiant flux intensity that reaches the Earth is just a small part of the luminosity. Okay, so that is the first part. So from this first part, we already have two terms, okay, which is luminosity and radiant flux intensity. Then we see the next point.
Are you muted on the recording?
Actually no, because if I press the microphone at the end, cannot work well. So that's why I have to off it. Okay, you can see here. So this is pictures that let you illustrate the situations. So you can see it here. The star is emitting the lights in all directions, and that's why they try to let you understand by forming a sphere. So once they reach the Earth, then they will form a bigger sphere. So try to imagine a bigger sphere, something like this, a bigger sphere. Okay, a bigger sphere. So this big sphere has a surface area. So which is A equal to 4 pi r square. So this is the r. Okay, so you just need to take the power. Just now we go through the formula. The power divided by the 4 pi r square. So of course the power at the numerator is the luminosity. Luminosity is power, right? So this is the luminosity divided by the 4 pi r square, and then you get the radiant flux intensity. So remember, so what we have on top, this is the luminosity. Okay, so this is the radiant flux intensity. This is the distance between the star and the Earth. Okay, so how do we apply this formula? It's very useful actually. If you are able to find out the F, imagine, let's say the scientist is here observing the intensity from the star, of course measure it through a particular instrument, and then you get the values of F. And then after that, you work out the luminosity by using a particular way where we will discuss later. Okay, so we work out the luminosity of the star. So you get this already. You get this also. And then you can use this formula to count the distance between the Earth and the star. Okay, so we can count it out. So we are able to find out the radiant flux intensity because we are on the Earth. And then there is a way to find out the luminosity. We'll discuss this later. And at the end, we can find this out. We can find out the distance between the star and the Earth. So we can do calculations to find this out. So of course, how to do it? We look at the next page. There we have more informations on how to find out all this. Okay, so now let's see this. So on this page, we have the inverse square law of flux. Okay, light sources which are further away appear fainter because the light it emits is spread out over a greater area. So try to imagine the star and the big sphere that I draw just now. So that is where I show the spreading of the light. Okay, so that's why the light is fainter. So when it's spread out for a long distance, and then the moment the light leaves the surface of the star, it begins to spread out uniformly through a spherical shell. So imagine the star and the sphere that I draw just now. So that is the concept that I'm trying to explain just now. The surface area of a sphere is equal to 4 pi r square. So we start thing again, the star and the sphere, 4 pi r square. So the r is here to here, that's the r. And then the radius r of this sphere is equal to the distance d between the star and the Earth. So let's say, for example again, let's say the Earth is here. And then the r, of course, the r is the distance between the star and the Earth. So by the time the radiation reaches the Earth, it has been spread out an area of 4 pi d square. 4 pi d square. Okay, so try to imagine the light spread out. Okay, an area of this amount. 4 pi d square. Okay. The d here is the distance between the star and the Earth. So where you can just use r. Okay, because basically r is also the distance d between the star and the Earth. So 4 pi r square and 4 pi d square is the same thing, because r is equal to d here. So as you can see here, r is equal to d. Okay, so then you have this, which is the surface area of the sphere. then the inverse square law of flux can therefore be calculated using this formula. So where this is the radiant flux intensity equal to the luminosity of the source divided by 4 pi d square. So that's why I said the scientists can find this out, and then there is a way to find out the luminosity. At the end, you can count the distance by using this formula, and this formula is called inverse square law of flux. Okay, so let's see the definition. F is the radiant flux intensity, or the observed intensity on Earth, which is watt per meter square. And then L is the luminosity of the source, which is this. The power, the unit is watt. This is the power, basically, the power of the star. So how we see the power, that is a way. So which we will discuss through. Okay, and then D, distance between the star and the Earth, we'll be able to count out at the end by using this formula. Okay, then let's see the assumption. This equation assumes the power from the star radiates uniformly through space. So that means, try to imagine through the pictures. So the star emits lights in all directions, like the yellow color that I draw just now, emit in all directions. The yellow arrows that I draw in all directions just now. So that is the assumptions. And then the next one is, no radiation is absorbed between the star and the Earth. Okay, so that means we assume there is no other planets that absorb the light. That is what we assume. Okay, we assume there is nothing that absorbs the light. So these are the two assumptions. And then after that, this equation tells us for a given star the luminosity is constant. So this is a constant. Okay, this is a constant. The radiant flux follow an inverse square law. That means this one, F, follow this formula. Inverse square law means they are having this kind of relation. You see there's a square there. Okay, so the greater the radiant flux, that means the larger the F measured, that means when this is big, the closer the star is to the Earth. That means the smaller the D. So which is kind of reasonable. If this F is big, then the D should be small. So let's say, for example, the sun. The sun is the nearest star to the Earth. So it is very bright. Hence the distance is very small. Okay, compared to other stars. Okay, so this is very small. Now, okay, again we have the illustration of the same concept again. So this is the star. So the stars, the lights spread out in all directions. So imagine the lights will reach a particular surface area of this size, and then when we go further to 2R, and then you can see that they show 1/4 there. They show 1/4. So what is 1/4 here? Actually is the idea of the square in the formula. Okay, so then when the radius is 3R, and then they show here 1/9. So again, this is the idea of the square, inverse square. Okay, so of course how we can just count it out in this way. So let's see some calculation here. You see our formula is F equal to L over 4 pi d square. So one of the easiest way to do it is to try to imagine the question said the luminosity is constant. So L is constant, and of course 4 pi is also constant. So I can just leave the constants on one side. So fd square equal to L over 4 pi, which is a constant. Then from here, right, I can form f1 d1 square equal to f2 d2 square. So I can form a formula in this particular way. So now let's say my d1 is equal to r. So try to imagine if d1 at d1 equal to r, and let's say the radiant flux intensity is equal to f. So at d2 equal to 2r, so I try to find out when the distance become 2r, so my radiant flux intensity will be what? So you want to find this out, we just use the formula here, the one that I put in box. So you can see how we work it out. F multiply with r square equal to f2 multiply with 2r square. So then you just count it out. f2 equal to fr square over 4r square, so f over 4. So you can see the radiant flux intensity is 1 over 4 times of the original, 1 over 4 times. So when the distance becomes 2r, the radiant flux intensity is 1 over 4 times. Okay, so likewise, if it's 3r, so let's see if I have f1 d1, f2, let's say f3 d3 square. Okay, now the d3 I use 3r, so you see the difference. So let's say this is f, this is r square, f3, now this one I change it to 3r, then you can get your f3. Your f3 is fr square over 9r square. Then you cut the r away, so you get f over 9. So you can see when the distance is 3r, the radiant flux intensity is 1 over 9 of the original. Okay, so 1 over 9. Okay, now this page settled already. Okay, let's see one question here. Okay, so this question we just discuss together. So if you know anything, you just tell me. So a star has a luminosity that is known to be this value. Okay, so this is the L. A scientist observing this star find that the radiant flux intensity of light received on Earth from the star is this value. So this is the F. But be careful, there's a small n there, nano. So that means not so bright. Determine the distance of the star from Earth. Okay, so we use the formula. F equal to L over 4 pi d square. So we use this formula. Then we just substitute value. Oops. The F. The L. Four pi and then d square. So we just want to find the d. So you can just use calculator and work out everything. So just let me know when you get the answer and you tell me what value you get at the end. there's a problem there. Should be 3.8 times 10 to the power of 18. By the way, is your substitution of value same with mine?
Yeah.
Okay, then I think maybe when you press something wrong or what, most probably.
Oh, my bracket is a bit off, so yeah, I get the same one as you now.
Okay, so that is the distance. Okay, so the thing is we already know how to get this. Is a scientist standing on the earth and measure the intensity of light received on earth. Now how to find the luminosity, so that is a way and we are going to discuss it now. So let's look at the next page to discuss about the way to determine the luminosity of the star. Okay, so which is known as standard candles. Okay, so let's see the information here. Standard candles. A standard candles is defined as an astronomical object like star which has a known luminosity. So we know their luminosity due to a characteristic quality possessed by that class of object. Okay, so that means there is a particular characteristics so that we know their luminosity. Okay, so let's say for example, right, example of standard candles are this one, surface variable stars. Okay, so surface variable star is what you can see here, a type of pulsating star which increases and decreases in brightness. You know, we have a song Twinkle Twinkle Little Star, so where the brightness is increasing and decreasing, that is the pulsating star. So over a set time period, okay, and then this variation has a well-defined relationship to the luminosity. Okay, so that means we can figure out the luminosity because it is getting bright and not bright in a particular period. So for example, it's something like this. Let me draw out a graph to let you imagine. Okay, so the scientists look at the star. Of course, when we look at it, maybe we just sing a song only. So but for the scientists, they draw a graph. So they put the radian, flux, intensity, F. They are using an instrument to measure the intensity, and then after that they draw the graph. Of course, the x-axis is the time in days, for example. Okay, let's say they observe something like this: not bright, then bright, then not bright, then bright, not bright, then bright.
Why is it like a curve and not like a spike?
It's just example lah. Okay, it can be a spike also. Actually, it can be a spike possible. Okay, so let's say it is like this. So and we look at the time span. Let's say in half a day it will become very bright and then come back to not bright again. Then in another half a day the same situation repeats, and then repeat again here, and then repeat again here. So by looking at these, then there is a way to figure out the luminosity. There is a way, okay? So of course the details will be like this. So I just give you brief idea only. So when they look at the time spans for the star to increase and decrease in brightness, and then we can get a graph. This graph is through observation of many stars. Okay, so the scientists need to look at this and that star. Imagine there are thousands or billions of stars. Okay, now they get a relationship. They draw another graph. Luminosity versus period days. The period days, for example, is like this. For this case, this is a period of 0.5. So the period is 0.5. Then it repeat again, so the period is 0.5. Okay, so you check the period, and then you look at this second graph, and then you can find out the luminosity, which is something like this. 1 to 100, and then there are data like this. This is after the hard work of observing many stars. Then they get this conclusion. Okay, they get this kind of conclusion where they form a straight line. Okay, they form a straight line. So let's say, for example, you see a star where the period is 20 days. And then you bring it up, then you bring it here, and then you check the luminosity. Then you will know the luminosity. And then you can use the formula just now to find out the distance between the star and the Earth. Okay. So I just put a little bit more information. So here is 10, and then the biggest value up there is about 10,000.
This is a fixed one.
Yeah, it's a fixed one. Like what I said, after the scientists work on many stars, they get this graph as our reference. So all the dots here are different. I label it here. Are different surface variable star, which means the star that has changed in brightness through a particular period. Okay. So we can get the luminosity. That is one situation. Okay.
So basically, they only get brighter.
Yeah, they will get brighter, then come back to a very dim conditions, and then get brighter again. So you just need to figure out the period, how long it takes to do that, and then you can figure out the luminosity.
Wait, but how come the down there the graph, it shows that it gets brighter and brighter, but the other one is quite constant? It goes back to the same one.
So you mean the graph here?
Yeah.
You see the label is period versus luminosity. Certain star take 1 day to change from this one to this one, from not bright to bright. Take 1 day, and then you look at this point. Certain star, they take 100 days to change from not bright to bright. And then you bring it up here, then the luminosity will be about this value. Yeah, it is this kind of idea on how we use it. Different star will have different period of time used to change from not bright to bright. So we observe that period, then we can find out the luminosity. So this is just for specific variable stars, which means just for those stars which is having change in brightness over a set time period. So, but you know, certain stars that don't have this situation, they are like same brightness all the time. So then we can't use this anymore. Okay, we can't use this anymore. So, for example, let's say this situation, we have the second type of star here, type 1a supernova. So supernova. Okay, so of course, supernova, what is that? Let's do some revision. Okay, so first you can see supernova without e here. This is a singular, so with an e over there, that is a plural. Yeah, a plural. So to know what is supernova, let's do a quick revision. They expect us to know from lower secondary for this supernova. Okay, quick revision here. It's about the life cycle of a star. So we have a stellar. You see, stellar. This word is here. Stellar again. Stellar, nebula. That changed to an average star. Average star is the star with moderate size. Massive star is a big star. So our sun is the average star. So then the average star will become a red giant. After many years, it will become red giant. But the massive stars will become a red supergiant. And then after that, it will become a supernova. So the supernova is this one. Okay. So then we have the red giant. Red giant will become a planetary nebula, and then followed by white dwarf. That's the end of the star. And then the supernova will end up with neutron star or a black hole. So our concern is this part, supernova. Okay, supernova, which is almost at the end of the life cycle of a star already. Okay, so which is white color. Okay, now let's see supernova, white color. That's why you can see here white dwarf. Okay, so you can see here type 1a supernova, a supernova explosion involving a white dwarf. The luminosity at the time of the explosion is always the same. So that means when you look at it as supernova, right, if the star is in this stage, which is supernova, then it has a particular luminosity. Okay, it has a particular luminosity. So we can figure out the luminosity at the end if there are these kind of supernova. Okay, so okay, I give you a little bit more information on supernova also. I just write it here, a short notes on supernova. So it is a star suddenly increases greatly in brightness because of catastrophic explosions that most of its mass. So this is the concept of supernova. Okay, so that's the thing.
Why does it become brighter after it becomes lighter? Why does like the weight correlate with the brightness?
You know, there's an equations, E equal to mc square. So the mass can change to energy. The mass can change to energy. So it's that kind of idea actually. And then when the mass change to energy, then that it make the star very bright. And that is supernova. Okay. Yeah. So when it is in this stage, which is supernova, then there is a particular value for the luminosity. And because of that, we know the luminosity, and then we can use the formula just now to find out the distance between the Earth and the supernova over there, which is the star. And we can find out the distance. Okay, so of course this is supernova, and if you are wondering, this is supernova, which is this idea, then what is type 1a supernova? So I have a short note also, so I put it here. Type 1a supernova. So this is separate, it's different kind of idea. Is a type of supernova that occurs in binary system. Binary system means there are two stars orbiting one another, in which one of the star is a white dwarf. The other star can be anything from a giant star to an even smaller white dwarf. They merge and create type 1a supernova. So of course, to understand all this information here, you have to look at the life cycle of the star at the same time. Then you will get some idea. And of course, you want to see the picture, you can always search from the internet. So there are all kind of videos on how they're formed and how it looks like. So you can see that also. Okay. So no matter how the main idea is, we look at the star, we see what kind of star is that, then we can find out the luminosity. Okay, this is what we call standard candles. So standard candles is formed by scientists after doing a lot of research. So let's see, we continue here. Using standard candles as a distance indicator. I know when we talk about standard candles, then we can find out their luminosity, then we can use the formula to find out the distance. So measuring astronomical distances accurately is an extremely difficult task. Okay, so that's why it involves a lot of calculation. A direct distance measurement is only possible if the object is close enough to the Earth. A direct distance measurement, not so easy one. So you want to use a space shuttle to travel from the Earth to another planet to direct measure the distance. That is very hard. So because of that, for more distant objects, indirect methods must be used. Indirect methods. So that, for example, the formula just now. That's the indirect method. Okay, this is where standard candles come in useful. So we use the standard candles to find out the luminosity. If the luminosity of a source is known, then the distance can be estimated based on how bright it appears from Earth. And this is the F. Okay, this is the F. So you get the luminosity, the L, from the standard candles. That means you see the features. Okay, then after that you estimate the brightness appears from Earth. This is the F. So you get the L, you get the F, then you use that formula to find the distance. And then astronomers measure the radiant flux intensity, which is the F. The radiant flux intensity, this is the F, of the electromagnetic radiation arriving at the Earth. So we can measure the F easily, okay, because we are staying on the Earth. And since the luminosity is known because of the standard candles, so as the object is a standard candle, the distance can be calculated using the inverse square law of flux. So this is the formula just now. So where the formula is, so again, the formula is F equal to L over 4 pi d squared. And then we can count the d. Okay, we continue. Each standard candle method can measure distances within a certain range. Okay, within a certain range. So collating the data. Collating means you collect the data, then you combine the data. Collect and combine the data. And measurements from each method allows astronomers to build up a larger pictures of the scale of the universe. You know, the astronomers is trying to figure out how big is the universe. They try to figure out, so they keep collecting data, keep doing calculation, and use different kinds of methods to work out the size of the universe. And at the end, it end up with this thing. This is known as the cosmic distance ladder. Cosmic distance ladder. Cosmic distance ladder is actually what? So you can just look at the picture on the next page. Okay, so let's see on the next page. So we can see the cosmic distance ladder in this way. So this is the pictures. So from these pictures, so this picture is called cosmic distance ladder. Just some brief idea. I write it up. Okay, so I just write it up here. Okay, this is cosmic distance ladder. So like what I said just now, the astronomer try to figure out how big is the universe, and end up with they build up something like this. Many methods has been used. So it's the successions of methods one scientist contribute one method and then many methods come together, by which astronomer determine the distances to celestial objects. You have to understand something like this. There are so many ways to measure the distance between the Earth and the stars. So different methods will have different range. Different methods, different range. So let's say, for example, one method can measure until how many astronomical units. So if it's further than that, then you have to use another method. It's something like that. So let's look at the details. Okay, we start from the bottom. As you know, whatever at the bottom is very close to the Earth. Then you can see it's getting further and further away from the Earth. Then we have to use different methods. Okay, so let's start from the bottom. Okay, so from the bottom we can see, we look at the words here first. A combination of methods involving standard candles allow astronomers to build out a cosmic distance ladder from nearby stars to distant galaxies. Okay, so we start from here. So first of all, you can see the Earth. They put a radar. Then they use the radar to emit some radiations, electromagnetic radiations, reach the Venus, and then come back. So this is like radar ranging. Okay, so a short note here. This way is called radar ranging. Radar ranging is useful. If it's too far, you cannot use this radar ranging anymore. Radar ranging is useful within 1 light hour. 1 light hour. Okay, so of course 1 light hour, you try to imagine what kind of concept is that. The light can travel at 3.0 times 10 to the power of 8 meter in 1 second. So in 1 hour, so try to imagine 1 hour is 3,600 seconds. So that is 3,600 times 3.0 times 10 power 8 meter. So this is the distance of 1 light hour. Okay. How far the light can travel in 1 hour. So it's a very big value in terms of meter. So radar ranging can do until this distance only. More than this distance, we have to use different methods. Okay, so that's why you can see it here. Solar system, 10 to the power of -4 light year. 10 to the power of -4 light year. So the Ly here is light year. They are trying to let you imagine how far is the planets. Okay, how far is the planets from the Earth, or how far is the planet, or how big is the solar system. So it's about this value, 10 to the power -4 light year. And you know, this is 1 light hour. 1 light hour. So 1 light year, we just count similarly. You know, you change it to 1 day, then you change it to 1 year, and then you can find out the distance. Okay, so try to imagine how big is solar system. I cannot imagine the value unless I go and count it. You know, I change it to 1 day, then change it to 1 year. Then will be very big. Okay, so for example, like in 1 day, you need to times 24. 24 times 3600 times 3.0 times 10 to the power 8. Then in 1 year, you need to times 365. 24 times 3600 times 3.0 times 10 to the power 8 meter. So it's a very big value. That is 1 light year. Okay, so let's move on. Let's go beyond of this. Then we have another method. So this is called parallax. Parallax. So parallax is also called stellar parallax. Stellar parallax. Okay, so this method, stellar parallax, is useful within 200 PC. So the PC here is what? PC is actually parsec. Parsec is a unit of length. So where 1 parsec is about 3.26 light year, and it is about 2.06 times 10 to the power of 5 astronomical unit, and it is about 3.09 times 10 to the power of 16 meter. So no need to memorize the value. I just put it here for you to imagine how big is the universe. Okay, so we are not going far yet. We are still quite close to the Earth. Okay, so this is the light year, and then this is the astronomical unit. Okay, so this is the method. Of course, here I put you some information. So 1 astronomical unit is here. From the Earth until 1 astronomical unit. So you can use radar ranging. From the Earth until here, this is 200 parsec. 200 parsec. So we can use stellar parallax, second method. What method is that? No need to know. Okay, so just imagine only. Okay, now Milky Way, which is further away. So how far is it? 10 to the power of 5 light year. Just now 10 to the power of 2 light year. This is 10 to the power of 5 light year. Okay, so the method that we can use here, okay, just a brief idea only. So there is the different method, which is called spectroscopic parallax. Another method. So this method is useful within 10,000 parsec. Okay, then we also have a graph here: relative apparent brightness, surface temperature. Okay, so we have this kind of graph. So they record down different kind of stars and their brightness. Okay, so and no need to know in details. Just roughly only. Milky Way, then another method. Okay, now let's move on. So now we have this one. This one we discussed just now. Luminosity versus period. You know, the star that is changing in brightness over a particular period. So this is the one that we discussed just now. This is the Cepheic variable star, and this is how far is it? Okay, so just now 200 PC, right? Until here is like 10,000 already. 10,000 PC, and 10 to the power of 7 light year. Then we use this way. Okay, this way we discussed before, the standard candle just now. And then this is for variable star. Variable stars. And this method is useful within 25 million PC. So variable star that we discussed just now, where you check how long it takes for the star to change the brightness, something like this. It's getting bright, then dark, bright, dark, bright, dark, okay, and so on. So the time span here is the period, and then you find out the period, then you put it here to check the luminosity. Okay. But this method is just for stars which are not beyond of this distance. If it's too far away, we can't use this method already, so we have to use different way. So we go higher up to the ladder. Okay, now we are a bit further. This is about 25 megaparsec. Okay, then we have to use a different way. So there are, you see, we have the something that we discussed before, type 1a supernova. So we discussed this before. So we need to know this supernova is useful within 1 million PC. Okay, then basically you can see what they draw here is two stars. You know, just now I give you the definition or the explanation of type 1a supernova, right? It's about two stars that merge and create type 1a supernova. So that's why you can see two stars here. Okay, then there is a particular graph which looks something like this. From this graph, we can check the luminosity. Okay, so of course in details, no need to know. And then this is another method, Fisher relations. So this method is for 200 megaparsec. So this method is called Fisher, which is useful within 200 million parsec. And when we reach until the highest level, this is 1 gigaparsec. Hubble's law. Okay, Hubble's law, you want to find the distance, so we have to use v, velocity, divided by a constant, ho. Okay, so when they are too far away, then we use this formula. Maybe there are other formula which will come soon. Okay, so far we have this until now. Okay, so this formula is roughly like this. We have velocity versus distance and then form a straight line from origin. And of course this one we can easily understand it in this way lah. V equal to HO times D. So this is the y-axis, this is the gradient, and this is the x-axis. So that's why we get a straight line from origin.
H naught is a new constant, is it?
Yeah, it's a new constant. Should be Haber constant if I'm not mistaken. So this method, the last method here, is useful beyond, so far lah, we claim it to be like this, useful beyond 100 million PC. Okay, so far we have all this. Until now we have all this. So from here you can see so many methods and so many efforts has been made to find out the size of the universe.